today's lecture will be about animation optimization for Unreal Engine 4 and 5. It will be probably useful mostly for the programmers that will operate in that area, people who work on general optimizations, also for the art part of the team, which plays within the anim blueprints and the meshes. So, Unreal Engine 4 and 5 is like the most robust and popular game engines in the world. Tons of AAA production is, if not made on internal engine, quite often uses either Epic product or Unity, of course. But in my opinion, regarding the 3D games and large-scale games, Unreal Engine is far better than Unity. So I'll focus on like a small fraction of its functionality in the area of management, calculations, rendering, and animating many repeatable objects on the screen, because it's like my kink within the programming area. So the general plan is to do some introduction, make the basic assumptions, and what is my main goal regarding the optimization stuff, and then talk about the engine characteristics a bit, then SignificanceManager, a bit about AI and navigation, then the core stuff, so the animation stuff, rendering stuff, then we'll do some summary, and there will be a time for questions and answers. You don't have to make any photos of the presentation or do the notes, because at the end you will see the link where you can download the whole presentation with the, like a cheat sheet, what can you do within the code and editor to implement by yourself those optimizations. Of course, it might not be like the universal stuff for every type of project, but I think some parts in some projects might be useful, so I hope you will enjoy it at least a bit. So let's start with the introduction. If you don't know me, so hello, my name is Grzegorz Wątroba. I'm a programmer for around 12 years now within the game development. I did a bunch of projects for different platforms using multiple engines and languages. Here's like a list of companies I was working for or I am cooperating with. And that's about it with the introduction. So let's explore basic assumptions and motivations for this lecture. So our basic goal is to have like 1,000 units on the level and up to 200 on the screen, because then it gets too dense. And those units are fully animated. They are modular characters, so they consist of many different skeletal meshes, and they are procedurally generated through some rules and algorithms, and every unit has its own schedule relying on the time of day and weather. Each unit can move around the entire city, react to player and interact with him. Of course, we aim for 60 FPS both on Full HD and 4K resolutions. So our challenges is to reduce movement cost, animation, rendering, reduce the calculation overlap, and keep units working outside the screen, and keep it all within specific budget to reserve resources for high quality image and artistic consistency on the screen. So we have to cut out all unnecessary stuff, and you will see that we have quite a lot of custom solutions, because we strictly know what we are aiming for, and that's why it might not be universal for you, because we use it in like a very specific way. You'll see in a moment how. All presented solutions are implemented, tested, and verified in our current project, Project Virtual. I want to emphasize that those solutions are not only my private ideas and implementation. To achieve those results, many former and current programmers from Fool's Theory were putting their hearts and souls into the project, and for that I'd like to thank them if somebody is here or will see this in the future. I would like to thank them for their effort, advice, and building foundations from which I could push those solutions a bit further. So let's describe some of the engine mechanics to be more aware of challenges and definitions that we'll face during this presentation. So engine is written in C++, has open accessible structure and code, it's very modular, allows to turn many stuff off and on. It's object-oriented, so it relies on actor-component relation, where like every actor and component has its own update phase at least, and everything is mostly built according to human intuition. So we have like something that has certain properties and we built in on it, but then we disperse certain data in the memory. So we can control each element on the object separately, state management, update mechanics, and we can even turn off garbage collector if we have courage for it. But remember, with great power comes great responsibility. And the biggest drawback from this approach is the execution overhead when we have those separate elements spread around the memory. So to avoid this overhead, we can do certain things. Either turn tick completely, turn on and off specific elements, and change update interval. So this is like the basis from we started doing some optimization. And while looking for optimization solutions to process repeatable instructions in a big scale, I explored 3 areas. So multi-threaded process is possible in Unreal in many forms. Parallel for async task or runnable structure are like the basic ones. Each technique is useful in different situations. So parallel for, the simplest one, allows to do multi-threaded processing within the array. It's worth using for large sets of data if task per array is quite heavy. Remember to never modify size of the array if you want to modify content of it. So if you want to change something that might step out from the element within the array, you should create a critical section by using mutex. I don't know if I'm pronouncing this well, but what the heck. Async task is more like fire and forget multi-threaded solution. We do not necessarily control entire process, but we can delegate feedback data to the main thread at the end. And frunnable is like the most complex solution to control entire multi-threaded process. And why am I talking about it? Because pathfinding is heavy. So remember, do not meddle carelessly within memory on threads different than main. And in most cases, you will get like the objection from the engine, but you can always go like all out and just turn off this this checkup within engine and see what happens. I encourage you, but in most of the cases, you will turn back to default settings. Other approaches that might be useful are data-oriented stuff. So ISPC from Intel, which is normally used within the engine. So it is a SIMD approach, so single instruction, multiple data. That way, for example, multiplication operations, instead of running only on one variable, it can be executed on set of variables at the same time within the same CPU cycle. This directly speeds up calculations and increases performance. So Unity uses for it burst compilator, and Unreal has ISPC. This uses both ISPC and ECS uses the power of CPU and memory prefetching. So it's like automated to some extent, automated vectorization. Entity component system is more of architectural design pattern where we organize data differently, granularize it, so the component is a single property and entity is like database entry index, so to speak, that filters the set of components needed to calculate specific functionality. One of the biggest profits here is potential to use SIMD to reduce tick, and since we have like a single tick for the entire set of data. We just need one system that ticks the data, and we do not spread this call among many components and objects. So by that we reduce overhead. Next thing we wanted to explore, and actually it's not easy because we don't have much time for it, is heterogeneous computing. So in regard to heterogeneous calculation, we use two different types of compute units in our cases. Those are CPU and GPU. And GPU can be utilized in at least two ways. So first is compute shaders, which use specific instructions separated from standard rendering pipeline, and provide calculations. Those calculations, if done on array-related problems, do get solved very well. And second are specific compute units present on NVIDIA. So those are CUDA cores and AMD cards, which are called compute units, if I remember. And each GPU manufacturer, Intel as well, has its own specific instructions, but OpenCL, so this API for calculations, utilizes all of them. So that's why we prefer using OpenCL to test certain solutions. Using those two solutions can be tricky, but when properly adapted to the problem, it can be very beneficial. Unreal has some convenient plugins for both, so there's actually an easy start if you really know what you're doing. Since we got to know the basics and the things we tried, let's focus a bit on measurements, because without them, it's hard to verify whether a given solution is actually worth doing, right? So a common way for people who play games is to measure performance by the frame rate, or frames per second. This can be actually a deceptive metric, because when gauging your application's performance, we should actually use frame time. If your game is running at 900 FPS, this translates into a frame time of 1.11 milliseconds per frame, and at 450 FPS, it gets like 2.22 milliseconds per frame. So this represents difference around 1.11 milliseconds per frame, even though the frame rate actually appears to drop by half. If you look at differences between 60 FPS and 56.25 FPS, this translates into 16.66 milliseconds and 17.77 milliseconds. So the difference here is the same, 1.11 milliseconds. But here, the drop in from the frame rate feels far less dramatic. So that's why, as developers, we should use the frame time to benchmark game speed, and don't worry about the FPS unless you drop down below the target. So focus on frame time to measure how fast your game is running, and then stay within your frame budget. So that's like, I think, the proper approach. And so to properly measure performance, we use three basic tools. So standard Unreal Profiler, which produces stat files. Through Profiler in the Unreal frontend, we can see the cost of instruction execution. We just need two simple commands, and that's it. So it's really useful if you're looking for the choking points within the project. Unreal Insights is much more advanced tool from Epic, and actually from what I understand, there is like it's recommended to get away from the standard front-end based stat files to actually use the Unreal Insights. And this allows us to connect to the editor both and build game to measure time cost ad hoc. So this works both for editor and cooked versions. We just need specific parameters so the game would extract performance data, and actually it gets much more measurements that I expected in the beginning. So it's really useful to try to utilize it. Also, last but not least, RenderDoc. So this is like external tool that can do the frame snapshot, analyze data stream, and measure instruction cost. Also, we can do it in editor, and on the build game, we can go to the point where we can measure cost of viewing single mesh. So it's like quite powerful and worth using. Measurements without testing platforms wouldn't make sense. So currently, while working at home, I had three different tiers of PCs, so to speak. So from 5-year-old mid-type grid to modern Apple mid-level configuration. So also we will test performance on 1 unit, 50 units, and 200 units on the screen. Times will be given in milliseconds and compared between unoptimized and optimized versions. Results can be sometimes fuzzy, and as you can see, we don't have the exact types of CPU and GPU to compare between the tiers. So it's not like lab quality level of testing grounds, but still it gives the proper, I think, the proper sense of how things actually work. Further down the road, we actually worked out currently the automated tests, the automated performance tests on build machines, which makes things a bit better and gives more reliable results. So there's that. We used some kind of probes that are spread on the critical in the critical points on the level, and then we gather up stat data from it, and then just organize it into some graphs which shows us after each build or after each day we can take the data and see whether we have progress or regress on the performance area. So it is important to remember to isolate to maximum functionality you are testing. So if you're testing some CPU-bound solution, try not to render anything at all, or at least turn off as most of the graphical effects as you can, and limit also all unnecessary fuss around other instructions. So try to isolate as much the solution you are focusing on. So after this theoretical solution, it's time to go to the main course. So first, the foundation of many optimization techniques in our project, SignificanceManager. SignificanceManager allows to register and calculate how important the object is within the current point of view. So the less significance, the less resources we can use for processing. It's crucial to write proper function to describe importance of an object. Position from the player is not enough. Aside from distance, it is advised to use camera frustum or sight range, since we see object in FPP game differently and isometric game differently, right? So system is very light. Quick to access gives a great foundation to optimize objects. It's not like the optimization tool itself, but it helps to produce those solutions. To configure SignificanceManager, you have to turn on the plugin, of course, and create on UGame viewport client, since it will make the whole project, the whole object to view relation easier to implement. The core of it is to feed SignificanceManager with data which will help us to calculate significance. And next, the object which we want to react to significance change has to be registered, right? So in begin play, preferably, but it doesn't have to be necessarily there. We should set up two methods: calculate significance and post significance. So here is the setup within the begin play, and how to actually implement that. Calculate significance takes data set up in viewport client and compares it within current object state. Then we calculate coefficient, which will describe the significance range of an object. And post-significance method allows to react to those significance changes and modify whether we turn on and off something, raise or lower tick interval, and so on. So we utilize that technique in many different game elements, from animation and logic to the priority of initialization, for example. That allows us to reduce the loading times, because we know at the start what significance has the object has. So after the initial preloading, when we have this begin within the object, we know how significant it is, and we can load additional data gradually from the center of the screen or from the view of the main character, main player, outside this circle, depending on the significance. That's why we can start a bit earlier the game, because all other data will load outside the screen, and that actually is also quite helpful for other stuff, which probably we'll address a bit later. So AI navigation, actually, this is like the less important part for it. However, since we use, since this is the part where it's always a choking point, because we have like 200 agents, or actually 1,000 agents on the level, and they all have to use the nav mesh and react with each other, bounce back, do the misses on the waypoints. We need to address that as well, because it affects other elements of the game. So we always can implement behavior tree, of course, and this is very versatile tool, but it's too complicated for our needs, because the only thing we need in our project regarding the NPCs is actually move from point A to point B and play animation. That's why it's great, of course, but completely unnecessary for us. So we create our own solution based on just specific objects which describe the path on the nav mesh, and then they store information if some unit reaches that area and has specific type of character or specific tag, play this animation. And that's actually serving the entire NPC logic in the game. It's really simple, and of course, since it's very modular and modifiable, we regulate this through SignificanceManager, so not every element necessarily ticks every frame, and that's why we get a lot of optimization bump here. Of course, the nav mesh is also used to some extent within our game, but also we have our own nav grid system which utilizes the nav mesh, but through that grid system we simplify the way the units move, and also we can simplify the way we set objects, because we can evenly spread out elements on the level. And also, since it's a grid, we can also simplify it to a simple table that can be utilized in Astar algorithm to get, for example, multi-threaded optimizations or GPU optimizations. So using this grid, although it has some overhead of the calculation, actually makes the life easier both for designers and for us as well. And the significance manager here actually is used for lowering tick update, tick interval, and turning on and off specific elements we don't actually need in the current moment. So that's why we get some optimization gain here. Also, within the pathfinding, like I said, we do some tests both for OpenCL, GPU-based solutions, and multithreading. But all in all, when we try to implement certain solutions, we get in the simplest multi-threaded Astar algorithm around 50–60% gain in comparison to the single-threaded one, so it's not that bad. However, we do know that we can do it better because we have something like mass system, because we switched recently from Unreal Engine 4.27 to Unreal Engine 5. And mass system is actually a full-on ECS solution dipped in the Unreal Engine. So for now, of course, it's experimental, has a lot of different problems, of course, but the first thing they actually produced within the mass system is units movement. So this actually works and doesn't need much of time to get implemented. We haven't fully integrated the system into the game. We're still testing out, but it's a really neat system, I think, and if it gets fully productional, it might give us a completely different level regarding the large-scale games and systems. So here, of course, not to complicate the nomenclature, because entity component system and especially component part means differently, has different meaning within the theoretical assumptions of this design pattern. And it differs from the meaning of the component within the Unreal Engine. That's why they changed the nomenclature a bit. So fragment is a component, set of fragments is a trait, and entity with trait is an archetype. And instead of system, because they have, for example, subsystem solution, they named it processor. So the relations within mass system looks a bit like this. So we have something like this. And to turn on the mass system, it's quite easy. We have just a few plugins, and the examples, for example, the test solutions from the matrix is a good starting point, although a bit complicated, but it actually works. So we based on that, and people already cut out the whole sprinkles from this project and made it much simpler, so you can find ready solutions from the people in the Unreal community to test out, for example, NavMesh navigation using a mass system, and it's giving quite good solutions. Still, we haven't implemented it strictly into the project. For now, we're testing. Since we want the stable solution that will work on more than one platform, we stick to the multi-threaded Astar because it's simpler and more reliable for a moment. So to see the differences here between single-threaded and multi-threaded solutions, let's see the performance changes here. So when we try to reduce overhead made by behavior tree, we see this kind of gains relying on a different set of scale. And yeah, so at the top in multi-threaded version, we can see that the gain is much more significant, but seeing the cost of a single unit, we have to face initialization costs, which becomes irrelevant as number of units scale up. So remember that if you have some small scale stuff, do not go over your head with multi-threaded stuff, because initialization cost of multi-threading might eat up any performance gain you might think. Now, the main course of our presentation, animation. And why am I focusing on it that much? Because our units have low needs in AI department, but it's completely opposite in animation area. Each unit has complex stack of animations to play, and we have to support it in efficient way with keeping appearance at the highest level possible. So animation blueprint is a specific asset type which we can operate comfortably with animation states, blend sequences, and animontages. It allows us to blend unit states fluently and join different kinds of animation. In a project, almost all units have one common anim blueprint, which makes it much easier for us to explore data-driven areas and multi-threading, since the core of it, so anim instance and skeletal mesh, actually are really focused on trying to use the internal ECS system and multi-threaded system. And it is visible within the code in 4.26 and 27, and even more in Unreal Engine 5. So bear in mind that AnimBP is not suited for calculations. If we can, entire computation should be present in anim instance, so the native class, and AnimBP should only react to data. If we do this properly, AnimBP will automatically use FastPath, which optimizes access to animation data. And in Unreal Engine 4, it is marked with this lighting icon, and that means that it is well used and properly used. And if you'll see that warning, like you can see in the lower picture, it means that you are trying to calculate something in AnimBP and you don't like it. And that means that you should try to do it differently if you want to have the most of the performance from AnimBP. Also, in project settings, we need to, of course, set optimize anim blueprint member variable access and allow multi-threaded animation update. It is crucial also to check use multi-threaded animation update and warn about blueprint usage. So this is the tick in class settings within AnimBP, and this points out where we have a problem. So this warn about blueprint usage actually makes a lot of helps tremendously when you try to find the choking points within the project of Anim Blueprint, and actually points out where the problems lie. Then the setup. You can see how the setup looks like in game mode, and how we can utilize specific settings for designers so they tune up parameters without programmer's help. Like I said, those codes and those blueprints and all of that, you will be able to download from the takeaway at the end of the presentation. You will see the link. So because now maybe it might not be clear enough on the screen, so you can read it out conveniently on your PCs if you download the presentation later. Okay, and this is the relations between anim instance and anim instance proxy, and how those structures work and how they relate in UnitBP. So this diagram should explain a bit. We have unit, which uses anim blueprint. Anim blueprint derives from native class anim instance, and anim instance contains anim instance proxy. And anim instance proxy is this data set that gets shared between threads on which anim instance is ticked. That's why there is this there's this pre-update phase when we should change the data, the update phase which should not take any data from the external elements and actually only internally process something, and then post-update method that should give information to the other classes externally again. And through that approach, we actually can tremendously optimize stuff, because the structure of anim instance proxy holds data and parameters for animation, and they are prepared before the animation frame, and then read all of this data and calculate within this anim instance code in non-blocking way. And after that, we have to synchronize stuff, and through fast path, we access data very quickly in a thread-safe manner within the anim blueprint. So that's why it is important to not only utilize anim instance and anim instance proxy, but also within the anim blueprint, we should get this data bind approach where you don't read data directly from the anim instance, but rather bind the data from anim instance proxy. There's this mechanism within anim blueprint that might suggest you to use it, or it can actually detect whether you have a custom anim instance proxy and allows you to click in data directly. And that's the proper approach if you have large-scale animations to maximize the attempt to use multi-threaded update. Now, when you have this all neatly set up, there's another element, which is budgeted skeletal mesh, and this is the most fun part for me. So budgeted skeletal mesh is an automatically connecting to significance manager kind of skeletal mesh, which based on previously established rules reduces time frame used for animations to save the calculation overhead. What is interesting, the system automatically distributes animation precision, which makes it much easier to test optimization. And this is quite easy to use, especially if you have already the setup for Significance Manager, because we use the same method to calculate significance for as for any other object in the game. And next is update rate optimization and immediate update checkup. So update rate optimization helps to improve the priority of update calls for a given animation and prevents animes from ticking too often. And actually this is really easy, it's just one flag you have to set in code. So enable update rate optimization, that's it. And the drawback of this is that if you have large number of animated objects on the screen and you set the budget too low, for example, if you set, I know, 1 millisecond only for animation tick, then you can experience on the screen that animations will be teared down, will update in a really creepy way or something. So you have to balance the budget you set if you want to use budgeted skeletal meshes. Still, it is very useful to combine all of those elements, because then through that you can actually have full-on really good quality animations within the area that is interesting for the player, and at the borders of the screen and further where players usually don't see and do not focus. You might have some cost cutting, which might be actually completely omitted by the player and gives us another milliseconds of performance gain. Also, if you're still experiencing lack of visible gains after all of those techniques I've described, look at needs immediate update method within the code. If it returns true, it means that given anim instance cannot be multi-threaded. So you have to go through all of those flags within that method and see where's the problem. And if some flag doesn't meet the expectations to return false, so the anim instance could be multi-threaded, you have to see whether the setup is wrong of the asset, or the you maybe forgot about some flag within the code. To find out why, do explore these flags, and if you fix them accordingly, then you have the you are sure that the anim instance can be multi-threaded. So within animation, let's see our measurements. So this is for Unreal Engine 4, and again we can see that single unit here doesn't. I forgot to change the language here. Okay, sorry. But in the last line, zisk means gain, and brak means no gain. So, okay. Still, the cost of setup and synchronization diminishes any gain if you have one unit, because the overhead of the general solution is a bit costly. But if you have a larger scale, the bigger scale you work on, the better gain you have. So the funny part is the last column, where you can see that the optimized version with budgeting gives always this 2 milliseconds, because we set it that way and we hold it that way, and 2 milliseconds actually works for our project. So entire animation tick in the most pessimist approach, the biggest scale we assumed needs only 2 milliseconds of animation tick, and actually it works for us. Looks great, and through that you can see that if we wouldn't use this optimization technique, we would have at least 2 times bigger animation instant update cost. So we have like 55% performance gain here, and within the Unreal Engine 5, some things were rewritten, and in that case, actually, the performance gain is a bit lower, because the single-threaded approach has been fixed to some extent. Still, the optimized approach gives the same results. So still, we have like 50% gain on animation tick. And let's go quickly, because we have a few minutes, to rendering. In the rendering area, we have lots of possibilities, but I'll focus on the quickest ones that we stumbled upon to reduce the scene rendering cost. And important aspect of rendering optimization are LODs, so levels of detail, which are the levels of complexity of the object depending on the distance from camera. So some time ago, it had to be done externally. Now Unreal itself can generate those LODs. It is especially convenient for skeletal meshes. And it is important to know how many levels we need and on which distance we can sacrifice visuals for the performance. In settings of each skeletal mesh, we can fine-tune it, so art director and team can establish some rules here. Still, it's quite simple to just set it up. And the crucial part of optimization is also not rendering objects. So we should avoid rendering stuff if we don't have to. Hiding those elements is called culling. Simplest is frustum culling, which works if it's not on in camera, we don't render it. So this is like the simplest one and default one. But there are cases though where the one object is completely overshadowed by the other and still within the camera. So what do we do then? We can use occlusion culling, which removes the object from rendering if it's hidden completely behind the other. It's turned on by default in rendering settings, so we don't have to especially tick it anywhere. We can also set in LOD settings at which distance given object will not be rendered as well. So this is more interesting part here. To simplify culling and calculation that go with it, we can use specific flag for mesh component use fixed skeletal bounds. It simplifies Mesh Collider, which allows us to save some time. And actually, from what I remember, we are taking it ad hoc at the farthest, the least significant bucket, because then it cuts out characters quicker from the screen. And of course, we shouldn't forget about the upscaling solutions. So both AMD and NVIDIA provide for Unreal very convenient plugins with a simple configuration, low effort demanded from a programmer. And both functionalities can be implemented quite quickly within Unreal Engine 4 and 5. In our case, they provide 50 FPS perspective no matter the chosen resolution. Overhead of the calculation is not lowered that much, but cost of rendering really makes a difference here. Without any quality loss or not so big quality loss, we can achieve 30% gain in performance, so to speak. Yeah, but it depends on the scene, because FSR in the first iteration was giving much better performance results, but it looks far worse than DLSS. Now FSR 2.0 looks quite good and almost the same as DLSS, not exactly the same, but it's less performant. So if we measure performance here, we can see that there's a gain around 27% in the biggest scale for Unreal Engine 4 when we used first FSR, and when we used FSR 2.0 on Unreal Engine 5, we have 25%. As you can see that we haven't achieved our crucial goal here, so the 60 FPS on 4K resolution, but we are getting there. We're only missing like the 5 milliseconds, and still we haven't used nanite and world partition, so we are on our way to go there. So let's summarize it. Techniques presented here might not be in entirety applicable to your games, but some of the solutions might be universal and some in proper context after appropriate adaptation. Remember to adapt to your genre of the game, experiment and measure performance to verify your theories. So this is like the general costs of the things we are working on, and you can see here how the calculation spreads out. So as you can see, the Significance Manager is really cheap, and actually, to my surprise, the culling in all of those calculations we were focusing is quite costly. So we probably should take a look there if we can do something more. Also, we need to work on animation update because we haven't polished up everything we can do there. Of course, pathfinding should be also reduced, and we hope to achieve it soon. Okay, so of course we are hiring, and also you can download the slides by scanning QR on the left and look for opportunities when scanning the QR on the right. You can always contact me in person. I'll be around. So yeah. Also, I will show those QR codes during the Q&A. So, but first, of course, you have links. I mean, yeah, of course. I mean links and to the source materials, and all of those materials will be available in the takeaway. So thank you for your attention, and you can always contact me in person through email and my socials. Again, yeah, you can scan out the QR codes or use links to download the takeaway with cheat sheets and everything. And now time for questions and answers. We have like 5 to 10 minutes. Yeah, so go on. Okay. 10, 9, 8.
So in your custom behavior tree, not behavior tree, but custom AI solution, how do you solve reactive problems of reactions of NPCs?
Actually, the reactions are made in a way that if our player steps into a certain area, then it wakes up this custom flow graph nodes, which then sets up the goal. The character goes into follows the character then on a separate tick and plays the animation or something like that. Any other? All right, so if you, sure, yeah.
If you know that your next project would benefit from those solutions, should you do it faster or later?
You mean knowing our next project?
Yes, maybe I will say it different. If you know that you will have like 200 plus NPCs or something like that, would you rather take those steps that you just showed us faster, sooner in the project, or
I know what you mean.
Yeah.
So judging from what our next project will be, which will be much complex in the AI area, we won't use that custom AI thing because it might be not sufficient enough for our needs. But definitely we will use this approach in optimizing animation tick, because it's like knowing what we need to do is like 30 minutes for us to set it up, and it's like really universal solution, since we know we will have again many NPCs and lots of animations. So that will definitely stay. Other things might not. Any other? No? So 10, 9, 8. 7. Okay, so if you have any other question, reach out to me. I'll gladly answer them. Thank you for your attention.